is going to involve a lot of judgment stuff. Like, for instance, you might get questions like, if you increase the sample size, what happens to the confidence interval? If you, it'll be material that kind of draws on the PowerPoints to a large degree, and the material in the PowerPoints might ask you to to draw some conclusions, given certain scenarios, probably short answers and so on and so forth. And they're also likely to be some calculations or some exercises that involve things that you can do with a simple calculator. Since you won't be working in a lab, you'll be working in a lecture room with the only thing you'll have available to you is a calculator. So I'm going to concentrate today on the problems that involve stuff that you can use a calculator for, assuming that that'll probably serve you the best when you take the lecture exam. You got 2 days to figure out, like problems that require SPSS or Excel and so on and so forth. So I think the immediate need right now, and a lot of questions I've gotten, involve basically how you use the tests and so on and so forth. So go carefully over those PowerPoints and look for things that, if you were making a test up, that you might ask about. Like, for instance, different kinds of tests. What assumptions would you make? For instance, when we're doing a t-test, certain situation, we would want to make sure that we had that the variables were independent, that they were randomly selected, and that the populations that they were drawn from were approximately normal, right? So that would be a list of assumptions, and I might ask you, what are the 3 assumptions associated with that kind of test? So keep an eye on that kind of stuff. Okay, so let's take a look at some basic stuff that I think that you'll be able to draw from to kind of get an idea of what people might ask you. For instance, you might get some questions about one-sided and two-sided tests and what a p-value means and so on and so forth. And a lot of that will be in the PowerPoints. I'm going to look at it from a little bit more practical perspective of what you see while you're doing this kind of stuff physically. Okay, so let's start off with these examples. I kind of stole from a website that has some really good tutorials that you might be interested. It's called statisticslectures.com. I'm going to type that in right up here. statisticslectures.com. And there are some really good examples there, including these. I took a couple of these examples. I like these particularly because they're kind of current, and I've been thinking about it since the Nets and the Knicks are both in the playoffs this year. Okay, so let's take a look at, for starters, one of the things that we've been working on is single sample t-tests, right? So I'm going to start. There's 2 ways that we might wind up with single sample t-tests. That might be when we're working with numerical variables, and it might be when we're working with proportions. So I'm going to start with numerical variables. It's a single sample test, and I'll explain why it's a single sample test. Okay, the question is, are the number of fouls called in playoff games different than during the regular season, right? Well, the regular season is over, right? So that we know how many fouls were called during the entire regular season. And during regular season, they called, let's say, I don't think this is a real number, but let's say they called 40.1 fouls per game during the regular season. That's the mean number. That's a population mean, because we have the entire population. We have every game that was played during the regular season. So now during the playoff games, maybe we only have data from 64 games. So this is a sample, right? So we would describe the mean of that sample of 64 games. And remember, on the exam, you might not get a sample size of 64. You might get a sample size of 8, so that you could, do the tests easily in class using a calculator. Or you might just, if you got a sample size of 64, it would be in this form where you just have this description, or you would have a paragraph from which you would have to draw this data. In other words, a verbal description as the way I'm speaking. Okay, so let's say during those 64 games, you had an average of 41.95 fouls per game with a standard deviation of 5.8. Now keep in mind, I didn't put sigma here, I put standard deviation because we got that standard deviation from this sample of 64 playoff games, not from the regular season games. Okay, maybe we don't know it, maybe we haven't calculated, maybe it's not available to us. So that's important because depending on where the standard deviation comes from, we might be forced to decide whether to use a t-test or a z-test. If I had told you that the population standard deviation was 5.8 and I used that instead, we'd be using the z-score for sure. If I tell you that our z-score our standard deviation comes from our playoff games, right, from our sample, well then you might have to use the t-test. The thing that would determine whether we use the t-test in this case is going to be the sample size. How big is the sample size? Well, the z-score that we need to prove this is bigger than 1.96, right? Because we don't have the population standard deviation. We only have a sample size of 64. If you looked up on the t-table for 63 degrees of freedom, right, might be something like 2.01 or something like that, or even 2.0, let's say. Okay, so if we use the t-score, that's what we would need. That's how far apart we would need our two values to be in terms of standard deviations. As it happens, we have kind of a general rule that if this sample size is over 30, well, we're just going to use the z-score. And the z-score tells us that we just need to be able to prove that these two values are 1.96 standard deviations apart or more. Right? So let's take a look at how this is going to look. First thing we're going to do is we're going to mention what our assumptions are. Again, randomly selected. In other words, we didn't take all Bulls games. We didn't take all Knicks games when we sampled it. We randomly selected. They're independently sampled, and that the number of fouls is normally distributed. I'm guessing at that. I have no clue. I would guess there's probably a good shot they are normally distributed. Okay, so now I'm going to, especially if you take them randomly, some teams get more fouls, some teams take less. But if you take them randomly across the whole league, might well be a normal distribution. Okay, so now I'm gonna take a look at this and I'm gonna say to myself, okay, so now I'm gonna have to find out what the t-score is. Are these really, or in this case z-score, are these really two standard deviations apart? Okay, so z is going to be equal to x bar minus the mean over the standard error for this distribution of 64 games. Okay, and what's that going to be equal to? That's going to be equal to, well, it's going to be equal to 41.9. Oh, I got a little ahead of myself a little bit there. H null and H alt. Okay, always nice to do this ahead of time, so you're not kind of taking any shortcuts. The null hypothesis. Anybody want to suggest the null hypothesis? Did you guys lose audio? Can you hear me? Okay, they are the same. Good. Okay, you can hear me. Good. Katie, are you back on? Can you hear me? Okay, maybe she dropped out. Oh, maybe she had a problem there. Okay, good. Okay, so null hypothesis is that they're the same. Okay, in other words, that the mean, there's a couple of ways you could say one is equal to the other. Another way of saying that is to say the mean is equal to what it is during the regular season, or 40.1. Right? You could also say x bar is equal to mu, I suppose. That would be a good way to do it. Okay, now what about the really important one, the really tricky one, is if I use mu is equal to 40.1, okay, or in other words, the mean for the playoff games is equal to 40.1, just like it is for the regular season games, then what's our alternative hypothesis? Our alternative hypothesis is, anybody want to hazard a guess? Right? It's not equal to 40.1, right? Okay, in other words, does not equal 40.1. Okay, Is that a one-sided or a two-sided hypothesis? Okay, two-sided. Good, excellent. Two-sided. Everybody agrees it's a two-sided hypothesis. What word in this description up here told me it was going to be a two-sided hypothesis? So these kind of questions that might help you out on the lecture exam just as much as they would on the lab exam. Okay, different, excellent, perfect. Thank you, Sonali. Thank you, guys. Okay, different is the important word there. The reason why different is an important word there is because all we're trying to prove is that they're different. We're not trying to prove, even though, see, it's one of the reasons it's always good to set up, an alternative hypothesis before you start working, or even maybe even before you start collecting data, is because notice the playoff games, the average was higher than the regular season. And once we get the data in, we're almost encouraged to say, oh, gee, it looks like, like the null hypothesis should be that during the regular season, during the playoff games, they give out more fouls, right? But that's not what we started with. What we started with is that they were different, not that necessarily they gave out more fouls during the playoff games or less or less fouls, but just simply that they're different. Excuse me. So that's where we stand right now, that they're different. So that's why we're doing a two-sided null hypothesis. Now, just to point out quickly, when we do a two-sided null hypothesis, whoops, let me get this out of the way. When we do a two-sided null hypothesis, I hope I didn't close that. Let me see if I can get that back. Where'd it go? Oops, that's not it. Where'd it go? Where'd it go? Where'd it go? Okay, hang on a second. Oh, I pushed it out of the way. I was hidden. You guys can't see that on my desk here, but there's a control panel on the side. Takes up that whole right side, so I can't see that portion of the page. Okay, so this is the possible distribution of all the possible outcomes that we might get if we were to do this analysis. Okay, and what we're saying is that during the regular season, they give out 40 fouls per game. Okay, so now we need to prove that during the playoff games, they give out so many more fouls that the number of fouls is so different than what they give out during the regular season that, and this is sample distribution size 64, by the way. Okay, they give out so many more fouls during the regular season that we are so far away, either above or below the mean during the regular season, that the odds of getting that result are only 5% or less. That's how rare it would be to get a result so different than 40. Okay, so in order to prove that, if it's a two-sided hypothesis, 5%, a z-score of 5% is represented, 0.05, is represented by 1.96. So this would have to be 1.96 standard deviations or z-scores. And this would have to be minus 1.96 standard deviations or z-scores. In a two-sided test, this is 2.5%. And this is 2.5%. Okay, now what would happen if this were a one-sided z-score? If this were a one-sided z-score, I'm going to see how far back I can go. Okay, if this were a one-sided z-score, I was saying that's just different, and we have a 5%, we accept a 5% chance of being wrong. Well, then I can put all 5% at the top end. I don't have to worry about the bottom end, right? Well, in that case, the z-score that I need to exceed to make this